So I'm doing an industrial PhD, and this means it's a quite applied one. I'm developing my research project at the company, the Meteorological Service of Catalonia, in collaboration with the University of Barcelona. And basically what I'm doing is to assess and, if possible, improve weather radar quality, data quality. And mainly what I do is to search, identify, and characterize those phenomena in weather radar images that do not belong to precipitation. And one of these cases is the sun. And today I would like to present a method that uses the sun interferences in weather radar data as a way to check the correct operation of the radar. And it's a method that was developed at the Dutch Meteorological Service, and we have adapted it and improved for fitting the characteristics of our radar network. Our radar network consists of 4 radars, of which only 3 are currently operative: Creu del Vent, La Miranda, and Puigtarcas. And today I'm going to show examples from Puigtarcas, but they have been applied to the 3 of them. And first of all, very briefly, how our radar works. It's in a fixed location, but its antenna, it's continuously rotating at constant elevations. And meanwhile, the radar is sending electromagnetic pulses of microwave frequency, and then listens to the echoes, which ideally come from reflection of this pulse energy by the hydrometeors present in the atmosphere. But sometimes the reflecting target might be another one, like, I don't know, birds, insects, mountains, and even the signal can come from other electromagnetic sources. And this is the case of the sun, which is also a microwave radiation source. When we look at the radar images, the sun interferences appear as these spikes in the direction of the sun. And the nice thing about this is that because we know the position of the sun in the sky, the elevation and the azimuth, and also the power level of its signal, we can use this data to check whether the antenna of the radar is correctly pointing and whether the radar receiver is well calibrated in power. So what we do is apply an algorithm to find these spike-like structures and some criteria for selecting the sun interferences. The most important of which is the sun proximity, so that we can get only the solar interferences during sunrise and sunset. And once we have these solar interferences, we can collect them, like here, for a whole month. We do it also in a daily basis, but here is for a whole month. And they display a very characteristic pattern as a function of their power, depending on the distance to the sun. This is very intuitive. The sun interferences which are closer to the sun are more intense. And they describe a parabolic surface, which is also theoretically modeled. The maximum of this parabolic surface, the position, will tell us the error in calibration, in pointing of the antenna, and its value is related to the maximum solar power, or the power at the top of the atmosphere. So we invert the model with the observations and get these 2 parameters, and if we do this on a daily basis, we can check whether the antenna is correctly pointing on the top, and we see for 4 months of data that there's no problem. The pointing error is always below 0.1. And for the power, what we do is to compare it with a reference from an astronomical observatory. And we also see that in this case it's quite well calibrated, and I can tell you that the method is reflecting also the in situ technical calibration, so this tells us that it's working properly. And this is an example of how to use a drawback for something good, which would be the solar interferences. Thank you very much.